Okay, let's go ahead and begin our T-notes for mechanics. And what is a force? A force is any push or pull on any object. It causes this object to change whatever it's doing. So if it's sitting still, it will move. Or if it's moving and then it stops. So it causes that object to change whatever state of motion that it is experiencing. Now, there are two different categories of forces, and these are contact forces and non-contact forces. I'm not going to go into each of them in detail, however, you are familiar with some of them, even if you're not familiar with the name of what it's called. So, for contact forces, there is friction, tension, normal forces, air resistance, applied forces, and spring forces. Now, for non-contact forces, there is gravitational, electrical, or magnetic forces. Now, one thing to note is that forces can differ in magnitude, and magnitude is either the strength or the size, the amount of force that there is. And one thing that you note is that a force can be large, and it's denoted by a very long arrow. So the larger the force, the longer the arrow. Smaller forces have smaller arrows. So not so much smaller, but less long, so shorter. Forces can also differ in which direction that the force is being applied to the object. So if a force is pushing on an object to the right, then you will see an arrow that goes to the right. To the left, the arrow will go to the left. Down as well as upward. Now there's also like diagonal. So all these forces, whatever the direction of the force is the direction of the arrow that it will be. Now, forces that a quantity with direction and magnitude. So we just described that forces can have magnitude and direction. If a quantity has both direction and magnitude, this is called a vector, and we denote it by an arrow. So if we have an arrow, it's showing a direction and a magnitude. For example, here are some vectors: displacement, velocity, acceleration, momentum, force lift, drag, thrust, weight. There is more, but these are just a few. For scalar, there is no arrow involved, and we'll go more into detail later at another time, especially if you're IB. Now, if a quantity has only magnitude, it does not specify direction of the force, then this is called a scalar. Length, time, area, volume, speed, temperature, pressure, energy, entropy, work, power. Again, these are just some. These are not all. Now, take a look at this picture with two people pushing on an object in towards each other. So, will this object move? Well, let's take a look. Here we have one person who is pushing to the right. So the force is moving to the right at what we denote as 20 newtons. This is the amount of force. This is the magnitude. This is the direction. So we know that the magnitude and direction, this is a vector. Here, on the right-hand side, we have a guy who is pushing to the left, 20 newtons. Now, will this object move? So we're actually talking about the net force. So if 20 newtons is going to the right and 20 newtons to the left, you would have a net zero, or a total movement of 0. So the direction of the object, it is not going to move. Now take a look at this wagon. And we want to know, does this wagon move, and in what direction? So here we have a force that is pushing the wagon from the left, so we're going to the right at 80 newtons. And over here on the right-hand side, pushing to the left, is a smaller force of 40 newtons. So in order to find the net force, we have to subtract, right? Because it's going in opposite directions. 80 newtons minus 40 newtons is 40 newtons. right? So, and what direction is it going to be moving? It should be moving to the right because the 80 newtons is greater. So the push to the right will make this wagon move to the right. Pretty easy, huh? So now that we know what net force is, let's just go ahead and write it in your T-notes. So net force is also known as a resultant. It's the combination. It's the combination of all the forces that are acting on an object. So what we just did before, the wagon, and then the two people pushing on an object. So how do you know when to add or when to subtract? So if vectors are going in the same direction, so let's say there were two people pushing on an object in the same direction, you would add the force. For example, if you had two people pushing the object at the same amount of force in the same direction, so you have 10 newtons magnitude of force in the direction to the right, you would have a total of 20 newtons to the right. Now vectors in opposite directions, such as the wagon, you would want to subtract the vectors. For example, you have the box down here, the object is being pushed to the left, 5 newtons of force, whereas there's a force that is pushing the object to the right, 10 newtons. So if it's in opposite directions, you would just subtract 5 minus 10 newtons, which would be equivalent to 5 newtons, and it would move to the right. Here's another example. So we have two columns here, and the way that you want to look at these two columns is that the first row, the net value, the net force of these two examples right here are exactly a net force of 0. So here we have two forces going in opposite directions at the same amount of force. So 10 minus 10 is 0, is the same as an object just sitting there with no force being acted on it. So both of these are an example of a net 0 or a net force of 0. In the second row, we have an object where the two forces are moving in the same direction. So if they're moving in the same direction, what do? We add them. So if we add them, we get 10 plus 10 equals 20 newtons. In the second row, second column, here we have the object with one force of 20 newtons. Both of these examples are exactly the same net force of 20 newtons. Down below, we have another object that's being pushed 10 newtons to the left, 8 newtons to the right, so that would be subtraction, and you would get a net force of 2 newtons, which is exactly the same as if an object only had one force pushing it to the left of 2 newtons. So I just wanted to show you that even though the amount of forces being acted on an object are different in these two columns, the net force, I keep saying that, net force is 0. So, or it is the same. So you have your two different examples in each of the rows. Now, you're probably wondering, what is a Newton? Yes, Newton is the scientist who worked on all of this stuff, and that's why we named this quantity a Newton. Newton is denoted by the big letter N, and it is the metric unit for force. And if you know anything about force, you've probably heard of this equation. Force equals mass times acceleration. Now, force is a Newton, so we denote it by the letter N, the big letter N, equals mass, which is in kilograms, and acceleration, which is meters per seconds squared. In physics, we denote it as kilograms times meters, seconds to the -2. So we always bring whatever's down below in the bottom part up. So that's what it looks like. So pretty much force is equal to the force it takes to accelerate an object weighing 1 kilogram. We accelerate that 1 meter per second each second. And so instead of always having to say these units of measurements, we just call it a Newton, 2 newtons, 3 newtons, and we know that that is translatable into the mass times acceleration. Now, another topic under mechanical or mechanics is tension, and you've probably heard of tension. Now, what is tension? It's pretty much the use of a string, spring, or rod, or some kind of mechanical device that stretches. And that stretching force, there are 2 forces that are involved. So here's an example. We have like a little spring scale, and at the bottom there is an object here that has weight, and it's hanging from the ceiling right here, or from some, I guess it is the ceiling, and it has tension force of 100 newtons going up, and it also has the weight, the gravity force, pulling the object down. Okay, and so the net force of this is 0, and the item is at rest. Now, mechanical equilibrium, there is a rule, and when the net force of an object is 0, we call this the state of steadiness. It means that the object is steady, right? And it applies to vector quantities. So it is denoted by sigma F equals 0. The sigma symbol stands for the sum of, and F stands for force. Now, here is an example which is mechanical equilibrium. So notice that there are 4 forces, right? There's 30 newtons to the left, 30 newtons to the right, and then 50 newtons up and 50 newtons down. All these are opposite of each other, so therefore the sum of the force is, the net force is 0. Over here, 75 minus 75 is 0, 50 minus 50 is 0. Both of these objects are at rest. They are at equilibrium, even though the forces are different on each object. So just know that the forces can be different and equilibrium can be met in different situations. Another force, support force, also known as normal force, is the upward force that balances an object's weight on a surface. So, right now, your computer is sitting on the table. It's the same as this, your physics book. Your physics book is sitting on the table. The table is pushing up with a force of 20 newtons on your book. And the gravity is pulling down with a force of 20 newtons. So therefore, the net force is 0, and you have the object sitting on the desk. This is an example of normal force. So when it is on a horizontal surface, the support force must equal the object's weight. So with this example, we already talked about the book, and the book pushes down on the table, and the table pushes back on the book. So it's like for every action, there's a reaction, and it's a equal reaction. Same thing with the spring. When you're pushing down on the spring is pushing back up on you. Just the same as when you're sitting in your chair, you are pushing down on the chair just as much as the chair is pushing up on you. Pretty cool. So let's go ahead and do a quick check to see if you understand. So let's say you are standing on 2 scales, 2 weight scales, and 1 foot is on each scale, and your weight is evenly distributed. Pause this and see if you can answer how each scale will read. Okay, so the answer to this is that the scale would read half of your weight. So whatever you weigh, half of it would be on one scale and half of it would be on the other. Now, the reason why is that because you are at rest, your net force is 0. The forces from both scales add to cancel your weight, okay? And the force from each scale is only half of your weight. Now, static equilibrium. is an equilibrium for an object at rest. For example, the hockey puck on ice. So when an object is just sitting there, the net force is, I believe this is supposed to say 0, so it's missing the 0. So you can go ahead and say that at static equilibrium, the net force is 0. So right now the hockey puck is on the ice and it's just sitting there. Nothing is moving it, nothing's happening. Now with dynamic equilibrium, it's a little different. Equilibrium for the objects, it's actually moving. The object is moving, but it's moving at a constant speed. So it's moving in a straight line. The net force is again 0. Example is an airplane flying at a constant velocity. So here we have the plane, and it's moving to the left. It's pushing to the left. You have the thrust going in this direction. You have the drag pulling you back, which is the net 0. Okay, or net force of 0, whereas you have your up thrust and you have your weight, which is pulling you down. And those also negate each other, so you have a net force of 0. So you're in moving at a constant speed. You're still in equilibrium. So an example of dynamic equilibrium is the pushing of an object at a steady pace. So for example, here's this man who is pushing at a constant speed, and notice that the object is being pushed along the floor, so there is friction involved, and the friction is moving in, it's moving in the other direction, so you have dynamic equilibrium. This is as long as you stay constant in like how steady you are pushing. Quick check. A bowling ball is in equilibrium when, go ahead and pause this and see if you know the answer. When it is both at rest and when it moves steadily in a straight line path. The explanation is that equilibrium means no change in motion, so there are two options. So if you're at rest, you stay at rest. You continue at rest forever and ever until something else happens. If an object is in motion, it will continue to be in motion at a steady rate in a straight line. If you are pushing a crate at a steady speed in a straight line, if the friction force is 75 newtons, how much force must you apply in order to move the object? Must be equal to 75 newtons. So the crate is in dynamic equilibrium. So remember that the sum of the forces need to equal 0. In order to make this true, you have to apply 75 newtons in the opposite direction that the force of friction is being applied. Now, your home fun is to answer the following questions. Go ahead and pause this, copy the questions down, and have the answers ready to show in class. Feel free to rewatch this video or to even use your Chapter 2 notes, which is where these notes came from. Okay, good job. Talk to you soon.